Well, it speaks for itself really. What an absolute beast of a synthesizer this is, all the way from 1973. You may have noticed we're not in the museum today, we're in my workshop. I do my own videos here on my own channel, there's a link below if you want to check that out. But the reason why we're here is because I'm going to attempt to fix this thing. It's feeling a little bit under the weather, and Look Mum No Computer has entrusted me to take a look under the hood. He does tell me that pretty much nothing works on it, so we may have our work cut out for us. But the plan is, once I fix this, he can do a longer video for you, telling you all about the history of this, where he picked it up, and actually playing it, getting some decent sounds out of it. And then we're going to put it in the museum, so you can come along and play it yourself. A brief overview though, this is the ETI 4600. It was designed by a chap called Trevor Marshall and was available as a mail order kit from the Electronics Today International magazine. Later it was adapted and sold in Maplin, which is the UK equivalent of Radio Shack. Back in 1973 this thing would have set you back about 500 quid for the parts, which, you know, is a fair investment, and you have to put it all together yourself. So they're pretty rare to come by, and with all of these DIY magazine projects, the build quality varies greatly. So it's going to be very interesting to dive into the electronics of this, figure out some of the circuits. Maybe we'll figure out why Trevor Marshall decided on some of the design decisions in it. We'll also look at some different diagnostic methodology of how to fix similar stuff to this that you can apply in your own projects, whether you're designing synthesizers, fixing synthesizers. This is going to be a pretty cool look into how these things were made 50 years ago. Yeah. Power comes in via this mini bulge-in plug, and then we're going to hook up a speaker here just to see what's going on. First, I want to listen through the 4 oscillators to see what's working. They're hardwired into the mixers. You see the knobs correspond, and to connect the mixers to the outputs you need to route that through the pin matrix. Oh yeah, this is pretty cool. Similar thing you'll see on VCS3, but of course this is a much cheaper alternative. It's got little pins like this, and you poke them in and it connects the outputs here of the different modules to inputs of the other ones and the actual main output there. So if we want to listen to the output of mixer 1, then we patch it into the output. There you go. So okay, we got some noise, that's good. Let's see, turn this down. Okay, so we're listening to this one. That seems to be working. Let's test across it. Oh, okay. So we got octaves, the tune, sync. Ooh, okay. So there's the fine tune, the coarse tune, and then when it's selected on, oh cool, all the waveforms work on that one, and the square wave there, we got a pulse width. Alright, okay, so we have one working oscillator, nothing coming out of that one, nothing coming out of that one. Oh, okay, some of the waveforms work on this one, but not the others. Okay, so we're going to tackle the oscillators first, and then we'll move on to all of the other stuff. Let's take a look at the circuitry. And first off, as my mate Cliff, who used to be a telephone engineer, pointed out to me, this is the most important tool in anybody's arsenal, the tea kettle. So while the tea brews, let's take a look at all of the circuitry. I'm quite partial to a Darjeeling with no milk, but feel free to throw abuse at me in the comments. It's all good for engagement. We actually have a copy of the original construction details. Awesome. Cost $150 back in the day. And sorry Barry, I didn't mention you earlier, alongside Trevor Marshall. So those are the guys responsible for designing this awesome synthesizer. Let's look at the first page. This is the construction details and all of the case and stuff, and having a quick look through this looks like a really fun project to have done back in the day. They go into quite a lot of detail about the thinking behind all of the design philosophy and stuff, and explain things about, you know, how humans perceive sound and how that relates to the electronics and stuff. It's really cool. All stuff about tuning and temperament, and if you flick over, we get to the first circuits here, which are the oscillators. We have diagrams here of all of the different wave shapes that you can get out of this circuit, as you would see them on an oscilloscope. Wave shapes are like the character of the sound, the timbre. So you've got sine, triangle, ramp or sawtooth, reverse sawtooth, and square. And you hear they get harsher in sound. So that's the sine. What we perceive as sound is just fluctuations in pressure waves in the air, and the more fluctuations, oscillations, per second, the higher in pitch we're going to perceive that sound as. And you move the air with a speaker. The speaker moves in and out and presses the air and creates the pressure waves, and the waveform just describes the way that the speaker moves in and out during a single wave cycle. So with a sine wave, over this period of time, the speaker is moving in and out smoothly. But over the same period of time, a square wave would be moving in and out sharply, and that describes the character of the sound. As is pretty common with analog synthesizers like this one, this has triangle core oscillators. So that means that the triangle wave is what's generated first, and then all of those other waveforms are then derived off of that by shaping it in different ways. So here, this section, this is generating the triangle waveform. Then down here we have a little circuit that transforms that into a square wave. This bit here transforms it into a sawtooth output, and down here we have the sine wave. And that's a good way of doing things, because all of the different outputs, of course, all derived from this triangle core, and so they'll all be exactly the same pitch, and all you need to do is have one voltage control circuit here to control the pitch of the triangle, and it will affect all of the other waveforms because they're derived from it. So we know that if the triangle wave doesn't work, none of the other waves are going to work. So let's set them all to the triangle wave, and okay, that's working. But then if we go to the square wave, is not working, the ramp is, and the sine isn't. Okay, so we know which sections of the circuit to now look at to fix the waveforms that aren't working in oscillator 4. Okay, so we're looking at this section of the circuit here, which is transforming the triangle wave output into a square wave output. And the triangle wave looks like this, and the square wave looks like this. So how are we doing that? That's like magic, isn't it? So we're going to be using a circuit called a comparator, and it's built around this operational amplifier here. It's got two inputs. You've got the minus here, which is the inverting input, and a plus, which is the non-inverting input. And you might guess from the name comparator that it's comparing the two inputs and outputting here on pin 6 and a decision, I guess. So coming in to the inverting input, we have our triangle wave. Coming in to the non-inverting input, we have the voltage set by this voltage divider here. We've got 0 volts coming in one side, we've got +5 coming in the other, so we can have anywhere between 0 and 5 volts. Let's imagine that we've set that to 2.5 volts, right? And our triangle wave is swinging between 0 and 5 volts. Okay, so this is the voltage threshold that we've set, which is going into the non-inverting, and the triangle wave is going into the inverting input. Okay, so when the voltage of the triangle wave is underneath this threshold here, okay, the output of the comparator is going to be high. When it crosses over that voltage threshold, it's gonna go low on the output. Okay, and we've then created a square wave here. And if you continue this across, as the triangle wave crosses this voltage threshold on the non-inverting input, it's gonna switch the output between low and high and low and high over and over, and that's how we've made our square wave. Pretty clever, eh? And you've got two transistors here. That's useful because we want our square wave to swing between 0 and 5 volts. The operational amplifier that we're using as a comparator will actually swing between -7 and +7 volts, because that's what it's being powered off, and it will swing between its voltage rails. Okay, so these are different types of transistors. One of them is an NPN, one of them is a PNP. The difference between them is that one of them switches on when the output from the comparator is high, one of them switches on when it's low. And you see here, this one is getting 0 volts going through it to that output when it's on. This one is getting 5 volts going through it when the output is on. They're alternately turning on, and that's how we're getting 0 and 5 volts square wave output there. So the problem could be anywhere in the circuit. The triangle wave might not be reaching this input, the voltage set by this voltage divider might not be reaching this input, the transistors might be having a problem. We're just going to probe around the circuit and see what is not matching the schematic. There's many different ways that you could probe into the circuit. You could use one of these things, an oscilloscope, so you can see on the screen the different waveforms and voltage levels and things, or you could use like a multimeter, maybe set it to the hertz setting so you're listening to the frequencies so you can see the oscillations in the circuit. But more and more I'm actually favouring using a speaker and listening to the circuit to diagnose stuff, especially, you know, as a musician I've trained my ears over many years to be able to hear those little nuances in the sound, and I find it's actually a quicker way than seeing stuff sometimes. Your ears are much more sensitive than your eyes. So I've made myself a little cable here, this jack cable, 1/4 inch jack cable. You've got the sleeve and the tip. The sleeve's connected to ground, and then the tip is what you're listening to. You can plug that into the speaker, and we've got a crocodile clip here which can go on the ground, and then we've got this probe, this multimeter probe, which you can touch the stuff and listen to it. This is the jack for the main output. Got to be careful, of course, because you can touch stuff that can damage your speaker, but that's why I have a little cheap practice amp like this, in case I touch the wrong thing and it messes it up. It doesn't matter too much. So before we even start, I've just noticed this cable here is loose, so that's a problem to think about a bit later. Let's concentrate on the oscillators right now though. So we are looking for IC11. If we look on this diagram here, we can see IC11 there, and so let's find that on the oscillator 4 board, which is going to be here, and you can see there it's got a dot on it just there, which means that the pin to the left of the top there is pin 1, and it goes around to pin 8. Okay, so if we want to listen to the output, that's pin 6. So 1, 2, 3, 4 underneath, 5, and then 6. Carefully put the probe on pin 6, careful not to short anything else. I'm not hearing anything. We would definitely hear it if it was switching between plus and minus 7 volts. So there's no output from the comparator, we're starting to narrow it down now to just this half of the circuit. Now let's listen to the input. We should be able to hear the triangle wave coming in to pin 2. Down here, careful. There we go. Okay, so we can hear that coming on in. Now I'm going to get my multimeter and test the threshold on the other pin 3, and then we can see, yeah, about 2.5 volts on there. So the threshold is set right. The triangle wave is coming in and crossing the threshold, but we're getting no output from the op amp. So we've isolated the problem potentially to the op amp. I'm gonna check that it's receiving power correctly. If the power is correct, then the op amp is bust. Pin 7 should be getting positive 7 volts, near enough, and then pin 4 should be getting -7. Yeah, so power's right. The issue must now be the op amp itself. We've checked the power, we've checked the inputs, we've ruled this out. It must be the op amp, so I'm going to replace the op amp. This is an LM301, so I'm going to see if I've got one of those. If not, I'll find an equivalent with the same pin out. There's different schools of thought about replacing parts in vintage synthesizers and stuff. Some people like to, you know, keep the originality and stuff. I can understand in a project like this. In reality, this won't make much difference at all to the sound in this particular case. So, you know, putting in a more modern chip that's probably going to be a bit more reliable won't hurt things. And I found some LM741s that will do the job. I'll take the knobs off here so that I can take the whole module out, way I'm not awkwardly trying to desolder this while it's in there. These are a collet type, so you pop the little cap off and then take a screwdriver and you can loosen that, and then the knob pops off. Like that, you see. If you watch the channel regularly, you know I like all the old telephone equipment, and so in my workshop I have the old telephone engineer's soldering iron holders and the -50 volt power sockets here. I can plug soldering irons into it, can plug these lamps into it, and even these test speakers. This is actually a desk from a telephone exchange in like the 1950s, so it's quite fun that we're still fixing electronics on it. Right, so we are going to desolder this IC, pop it out and pop a new one in. I've turned the power off, of course. Just heat it up and suck it away with this. And we should be there. Sometimes the trick to desoldering something is actually adding a little bit more solder. It just sounds counterproductive, but if your solder has a flux core, then that flux will help the old solder flow a little bit better, and you'll be able to suck it away. Okay, now that is loose. There we are. Let's plop in the next one, making, of course, sure that it's up the right way. What I'm going to do is put a socket in so that if it ever does go again, we don't have to desolder it. Put one nut on just to hold it in there for now. We're listening to the triangle wave coming out of oscillator 4. Let's switch it to the square wave and see if it works. Yeah, there we go. Awesome. So that's one thing fixed, but the sine is still not working, so now we need to look at that. So this here is a resistor ladder. It's a voltage divider network. It's a load of fixed resistors that work together to divide the voltage between the top and bottom of the ladder, the plus 7 volts here and the minus 7 volts here, and they work together in series. So all of these ones against this one for this nodal point, this tap off of the ladder, all of these ones and those two added together to divide the voltage at this point to give us a series of increasing voltages off of these taps. And if this ladder was from 0 volts to 8 volts and all of the resistors were the same value, it would step up like 0, 1, 2 volts, 3 volts, 4 volts, 5 volts, 6 volts, 7 volts, 8 volts. But you actually have different values of resistors. This is a 270 ohm, this is a 56 ohm, 120, so you're not getting equal steps here in between the taps off of the ladder, and that's important for the job that it does. So if you look at the components that are directly connected to the taps off of this voltage divider, they are diodes, and diodes only conduct current in one direction, and in the conventional model of thinking about current flow, that is conducting in the direction of the arrow, and the line there, you can imagine that stopping electrons flowing in this way. In reality, electrons actually flow from negative to positive, not positive to negative as we normally think of it, but what happened yonks ago, they got it wrong, but it was already too late by the time they figured out that, and so we established the conventional model of thinking about current flow from positive to negative. Anyway, all of that is an aside to say that you need a voltage difference for current to flow, and so if this point on this side of the diode is lower voltage than the point the other side of the diode, then current is going to flow through this diode. And if it's the other way around, this voltage point is higher than this point, then the diode is going to block the flow of current. Okay, so as that triangle wave rises and falls in voltage, it's going to start meeting the voltage thresholds for these diodes to start conducting, and so in conjunction with these resistors here, it's actually forming a voltage divider, another voltage divider, and you can think of that current flow away from the triangle wave coming in here as it kind of leaking away the voltage. And so if we do a very, very basic paper simulation of this, starting at 0 volts, as the amplitude of the triangle wave increases, it's going to meet the voltage threshold where this diode starts conducting, and that forms a voltage divider. So it's going to attenuate the amplitude of the triangle wave, so it's going to look more like that, and then these diodes are going to start conducting and have even more influence, i.e. attenuate the signal even more down to here, and then as the wave starts falling, it's going to have the reverse process is going to happen to the point where you reach 0 volts to start going to the negative voltages, and where these diodes start conducting, and the same thing happens in the negative domain, and that carries on like that. And the advantage of doing it like this, not using like a filter or something, is that it's going to output the same amplitude of sine wave regardless of the frequency that the triangle wave is coming in. Then on the output here we have another inverting amplifier with a whole network of resistors here, and so that you can offset and scale the output. It is a complicated one, this, but I do think probably the coolest circuit in here. Not an easy thing to do, turn a triangle wave into a sine wave that doesn't diminish with higher frequencies. And so as before, we're just going to work our way through the circuit, tracing it to a point where it's not doing what we should expect it to do, and hopefully that will indicate what's going wrong, which component is bust potentially. Okay, so we want to listen first to the output of IC9, which is pin 6. IC9 is there, so let's find that on the card underneath this trimmer here. So if we turn up the speaker, and then we can listen to pin 6. Okay, we are not hearing very much. That's probably an indicator that that op-amp maybe has also gone. Let's listen to the input. Actually, no, it's an inverting input, so we're not going to be able to hear that. Let's listen to the other side of R28, which is the resistor under it, just to make sure that it's actually getting... Yeah, the triangle wave is coming into there, and it's not coming out the other side of the op-amp. It should actually be louder coming out the other side of the op-amp, so we're definitely not hearing it. So that is pointing towards this op-amp here being bust. The reason why I didn't listen to this point is because it's an inverting amplifier, so through this feedback loop here, it's creating a virtual ground there, so there'll be nothing at this point. Good to know all of your basic op-amp configurations, like inverting, non-inverting, differential. There's the triangle. Hey, the sine is now working. We got sine, triangle, saw, reverse saw, and the square wave, all of it. And yep, the pulse width works on that. Yep, tune and the octave. Awesome, cool. So we have 2 working oscillators now and 2 that are not working at all. So we're going to look at the triangle wave circuit. And I just checked that the problem isn't with the mixer. It could always have been the stage after, and that's why we weren't hearing it out the output. So I probed on the circuit, and definitely the triangle core oscillator is not working, so all of the other ones down the line are not working either. So this whole section up here, this is everything involved with making the core of the oscillator, the triangle wave. Okay, and the first section we're going to look at around here, this is in fact all of our pitch control information coming in from various different sources. We've got the octave switch, can you see around here? You've got a potentiometer here, all controlling the voltage level that's getting kind of summed together at this nodal point here on the inverting input of this inverting amplifier. Okay, and so all of these different things around here, these are all having an influence on the voltage that is getting output added together and output of this amplifier. And because it's an inverting amplifier configuration, you are actually getting the reverse polarity of what you put on the input. Okay, so if you put a positive signal into this inverting input, you're going to get a negative voltage on the output. Okay, and so we also have another inverting amplifier here, which is being fed by the output of this amplifier. So the outputs of these amplifiers are going to be the same, but in opposite polarities. One's going to be positive, one's going to be negative. Okay, so these feed down to this point where they go through switches, and that's where we need to talk about this whole section here. This is what is controlling these 2 switches. Okay, so these switches alternate, so only one is on at a time. Okay, so at this point of the circuit here, you are actually switching between the negative and the positive version of the voltage at this point, okay? And you'll see why we need to do that later when we talk about this integrator, okay? This here is a comparator, just like we talked about in the square wave section here. This is implemented with an op-amp. This is implemented with discrete transistors. This is a special type of comparator called a Schmitt trigger. That means that unlike the comparator that we looked at before that has a single threshold that changes the output state as you cross over it, this type of comparator has two thresholds, an upper and a lower, okay? And so if you can imagine the voltage crossing that threshold, okay, at the top, that switches the output, okay? But if that voltage on the input were to go low and dip below this threshold, the output state would not change until it crosses the lower threshold here, okay? So there's this window in the middle of these two thresholds where the output state is not changing. The output of that comparator is feeding these inverters, and the output of this inverter is actually what's going across and controlling these switches. One of them switches on when the output of this inverter is high, one of them switches off, okay? So they're only on alternately, okay? So now the only section that we've got left to talk about is this whole bit here in the middle, which is receiving a switched negative and positive supply as the point here passes above and below the threshold set at this comparator. Yeah, okay, so this is an integrator. This is another different type of operational amplifier configuration. Slewing, which means slowing down the rate of change between this square wave. So instead of it switching rapidly between low and high, it's smooth, it's over time taking longer to reach the low and then high point. So you can see there, as I'm drawing it, you're getting a triangle instead of the sharp square, okay? So this integrator here, built around this operational amplifier, is performing the mathematical operation of integration, and we're going to get into some maths, but it's actually quite interesting. Math was my worst subject in school, and I think it puts a lot of people off getting into this stuff, but it is quite interesting, I think. What you can do with integration is to find the area of a shape. So say I have a graph here like this, right? And we've got a fixed level here, which is analogous to our voltage coming into the input of this integrator here, right? We can use the integration function to find the area, the increasing area underneath this line on the graph over time, okay? So as we go along in time, this area under the line and to the left of my screwdriver is increasing, okay? So you could plot that on a graph like this, okay? So as you're going along in time, this area in here is increasing, okay? So you're getting a rising linear line on a graph, okay? And this is how we're starting to turn this square wave that's coming out of here into a triangle wave. It is important to note, however, that this op-amp integrator is actually going to output a negative integral, and that's because this is a effectively it's kind of like an inverting amplifier. You've got a negative feedback loop here, and op-amps, what they try to do is they just want both of their inputs to equal the same thing. They want them to be the same voltage. So the output of the op amp will feed back through this this loop here to try and counteract whatever is coming in here, in this case to make it equal ground. What you need to know is that if there's a positive voltage on the input, the output is going to fall down into the negative domain, and if it's a negative, it's going to rise up into the positive voltage domain. Okay, so let's talk through this step by step and see which bits are affecting which and how the oscillation is actually created. Okay, so we're starting off with one of these switches on, one of these switches off, and that is applying either constant negative or positive voltage to the input of the integrator. That's going to cause the output of the integrator to either rise up in voltage or fall in voltage, and at a certain point it's going to reach the threshold of this comparator, which is going to change the output state of the comparator, and in consequence this inverter to either a high or a low state, okay, which is gonna go back to these switches and turn the one that was turned on off and turn the one that was turned off on. Okay, so we're gonna get the changing state of voltage from positive to negative or negative to positive on the input of this integrator, which is going to change the direction of either the rise or the fall on the output, okay, until it meets the higher or lower threshold of the comparator again, which again changes these switches around to on or off, which is going to repeat the whole process. And so you're getting this feedback loop, okay, which is creating the constant oscillation, okay. It's unstable. This circuit is unstable. It's going to constantly change between one state or the other, and that's how you create the oscillation. The reason why this integrator is really, really useful is because if you think about it, right, if you've got an area that you're measuring here against time, okay, so this area, as you progress in time, is going to give you a rising linear output, and so if you increase the voltage on the input, okay, so say it's this level, this this area here that you're measuring is going to be bigger, right? So this line is going to be steeper, okay. So that means that it's going to meet the threshold of the comparator sooner, okay. Say the threshold is here, okay, it's going to meet it at this point in time instead of at this point in time. So this solid line, okay, that's measuring the area underneath this point against time, is going to oscillate at this rate, okay, but this dashed line that's measuring the area underneath this point is going to oscillate much quicker, okay. And so that is how the voltage control from our keyboard or other sources is influencing the frequency, the pitch of the triangle wave that we're getting out. It's very, very clever. It's a bit complicated. I really hope my drawings are good enough for you to kind of get your head around it. But yeah, pretty cool, isn't it? So how to go about diagnosing this? Well, so far everything has been problems with op amps. So I'm kind of looking at these op amps. Clearly the output of this one is it's definitely not oscillating, okay. So that could be multiple different problems. It could be problems with this that is causing the switch not to switch. It could be the switch itself not switching. It could be any of these op amps not working. So I just need to really work through it and I think I'm going to start with these ones, rule all of this out of it, make sure that we're getting the right voltage levels that we should expect on the outputs of both of these op amps, and then gonna look further down here, see if the Schmidt trigger is working, the inverters, then see if the switches are turning on as they should with the voltage level that is coming out at this point, and follow it that way. Okay, so I tested the outputs of these two amplifiers, and they're doing what I should expect. I tested the resistance across these switches to see which one was on. Only one of them is on. So if there was a problem with a switch, I would have expected to see both of them off or both of them on. So it's perhaps pointing towards the fact that these switches are okay. Obviously none of this isn't changing, the comparator is not switching, so now my theory is that this IC4 is not working. I reckon that's it, another bust op amp. At this point maybe it's a good idea to actually change all of the op amps in here. These LM301s don't seem to have stood the test of time. Okay, happy days. We've now got a triangle wave coming out of there. Oh, we got a sine wave. We got a ramp, and a square. And the pulse width works. Amazing. Okay, awesome. We have 3 working oscillators now. Let's tackle the last one, oscillator 3. Maybe it's the same problem. Okay, yes. Same problem with the triangle wave, and now awesome, all of the other ones are working. And the sync's working as well. Okay, great. Okay, awesome. We have 4 completely working oscillators. Oh yeah. The section that we didn't look at was this bit of the circuit here, which is outputting the sawtooth wave. It's pretty interesting. It uses switches just like these switches here, which is a good idea. They're integrated in the same circuit, IC3. You see, this is units 3 and 4. So if you've got an IC with 4 switches in it, you may as well utilize it to its fullest potential. So they've used all of the switches in that IC here. So yeah, I think it's a good way to do this sawtooth output. If you want to see and read how this works, then I have put a link down below to this document, and you can read through how it all works on here. It's pretty interesting. So now we have a load of calibration procedures to set the amplitude and adjust some of the wave shape. I do need an oscilloscope to do this. I was going to use this beautiful one that I picked up at J. Burkitt's, which is a shop in Lincoln, one of the last surviving radio spares shops in the UK. This is an amazing hand-built oscilloscope. You can see the labels there, but I forgot it's only AC coupled, this one, and it doesn't have its own internal oscillator for the horizontal axis, which is slightly annoying. I was using my modular case here, so we're going to switch over to one of the other oscilloscopes, and we'll get calibrating. Funny enough, I did actually come across an advert in old electronics magazine for J. Burkitt from the 80s. It was run by John Burkitt back in those days, and now run by his lovely daughter Judy. Go pay them a visit. It's the coolest shop in the UK. John used to fit the electronics in Lancaster bombers back in the day, and I have a whole box full of avionics that I mostly picked up from their shop. This is the Maplin synth, and Maplin no longer exists. I think it's even more appropriate to big up places like that. So please go there and buy things and keep it alive, because it's a cool place and it's a bit of a pillar of the community, to be honest, with the ham radio community. Yeah, so I've hooked up the old oscilloscope here, and I'm gonna run through all of these procedures to calibrate the oscillators. Right, so we got the sine wave up at the moment, and if I adjust this one, it should make it much sinier. It's quite triangular at the moment. Let's adjust that. Oh yeah, it is rounding it off quite well. Gone a bit too far there, and then yeah, that's looking quite good, that. Bit of a race against time here. My oscilloscope is slowly dying. The brightness is getting less and less. So I'm trying to set this now so it's peak to peak 5 volts. That should be RV15. I just got to find that. And so that the oscillators will actually track in tune with the keyboard. To do that, I really need to look at the keyboard first to check that it's outputting the right stuff to the oscillators. So that seems to be the next thing to look at. Okay, well, I hope you've enjoyed this part of the repair of this amazing synthesizer. We're going to carry on and get it fully working for you. So if you want to come and use this, you come and visit us at the museum. We're in Ramsgate. It's just a short hop on the train down from London in the south of England, and you can support us to do more videos like this, because all this stuff takes a lot of time and effort, by joining the Patreon. There's a link down below, or you can make one-off donations via PayPal on the website, or YouTube super thanks, or buy us a coffee. There's links down below for that. You can buy sample packs. There's recordings of all the cool things around the museum that you can chop up and sample and use in your music and stuff, and it all helps with the engagement on YouTube if you like and subscribe and comment, and you know the whole spiel, but it does make a difference. So and we like to hear from you. We'd like to hear what you think of the videos, whether you want us to do more parts of this repair. Let us know if it's useful for you. And if you can't make it to the museum during the open hours, or you want to book a private session so that you can do recordings at the museum, have the run of the place and use all the synthesizers and machines and stuff, there's more information about those private sessions on the website. I probably misspoke at points, so feel free to correct me in the comments, and any advice for me or for other people, feel free to share that as well. I'm sure people will appreciate it. So thank you very much, and we will see you in the next instalment.